Pump it up. Data mining the water table, oral presentation. We'd like to start off by thanking Mr. Wedding, as well as the rest of the executive team and board of directors of Daft Pumps for their time, consideration, and insights into this project. We hope that the end result is something that you guys find worthwhile of your time. We'd also like to recap who's on this team. The team includes Daniel Butler, Austin Harrison, myself, Francis Carr, and Tyne Hutchison. So here's our plan of attack. Number 1, why are we even doing this? What was the reasoning behind it? What was the purpose? Number 2, what are we working with? What's the data provided? What were we allowed to use? What weren't we allowed to use? Number 3, the process. What was our process throughout this? From exploratory data analysis to data cleaning to potential data transformations, and finally to data analysis and recommendations and conclusions. Number 4, the tools. What tools did we use for this project, including R and Python, and what worked better? Number 5, the models. What models did we run, including XGBoost and Random Forest, and how'd they rank up against each other, and what did we end up using? Number 6, how'd we do? What was our final ranking on the leaderboard in Driven Data? What was our final classification rate, and what does the classification rate mean? Number 7, did we meet our goals? We'll recap on the 3 goals that we set ourselves up for and whether or not we met them and or exceeded them. Number 8, what does this mean? What are the recommendations we have? What were the limitations we have? Do we find this project worthwhile to pursue in the future? And finally, what's next? What do we see as future work based on what we've done so far? So let's start off with why are we doing this? As you all may know, water is a scarcity for close to 1 billion people in the developing countries. Because of this, the Tanzanian government is working to optimize operations of local water points and or water pumps to help citizens obtain better access. Daft Pump's plan is to use the data provided in this project, clean it as necessary, and transform when necessary, and then optimize the best model to classify water points based on functionality. Just as a reminder, functionality is based in 3 categories in this project: functional, functional needs repair, and non-functional. Optimization of a model classification could eventually lead to basing the repairs of water points to be on predictive analytics, which could end up meaning fixing the water points before they even break. What does all of this mean? Less problems with the functionality of water points leads to more access for these people.
Hi, this is Dan Butler, and I'm going to talk about what we are working with, along with the process that we followed. The data consisted of 39 columns and an identifier column. These columns were split generally into 3 categories: information about the location of the well, latitude, longitude, altitude, and various text identifiers. Second, we had information about the building of the well, which included the funder, the installer, whether or not there was a public planning meeting or permit, and the year of construction. Finally, we had information about the operation of the well, which included the management and its structure, the price charged, the quality, quantity, and source of the water, along with how it's extracted. This data was split into 3 categories: functional, functional needing repair, and non-functional wells. Functional represented the highest portion of the wells with 54%. Non-functional had 38%, and functional needing repair represented about 7% of the data. Looking at the map, you can see that all these wells in their different states are spread throughout the country, although there do appear to be some pockets of high percentages of non-functional or functional wells. Next, there was a large amount of missing data. Many columns had missing data. We noticed that there were 4 columns that didn't appear initially to have any missing values, but had a large degree of 0 values. And the 0 values appeared to represent missing data. Looking at these columns in a map overlay, you can see that generally wells that missed these 4 pieces of data, or that had 0 values for these 4 pieces of data, primarily fit within 3 regions in the map. This informed us in terms of how we needed to replace these values and allowed us to provide better imputed or estimated values for the missing data than if we had assumed that they were just missing at random. Per the competition rules, we were only allowed to use data in the data set for generating models. We identified some potentially important data outside of the data set, including funder category, which split the funders based on their source, like a government or non-governmental organization or nonprofit, and an elevation based on the GPS lookup. Because these were not allowed in the modeling competition, we didn't include them in our final model submission. One of the first things we did was run the data through a random forest. We will later explain what a random forest is, but one byproduct of a random forest is that you can see the importance of different variables. If you look here, you can see the quantity group is marked as the most important, followed by latitude, longitude, and quite a few other variables. This was important because, for example, latitude and longitude was missing quite a few values, about 1,800, and as we noted before, construction year, population, and GPS height had significant amounts of missing data. Using this information, we were able to quickly identify the values that were most important in this model and spend more energy replacing these values. The other thing we did was made the data easier to work with. An example of this is age, a column we created which was the difference between the construction year and the date recorded. Next, we changed many of the column values by performing a transformation. This allowed them to behave better when modeling. You can see in the left graph that population has a spike at 0, or values close to 0. When we changed the log of the population, we got more of a normal curve, although there were still a significant portion of 0 values. Finally, we added the column month recorded. Month recorded is important because some of these wells might depend on weather patterns to predict whether or not they'd be marked as functional or non-functional. A well may only appear to work for certain seasons, and because of that, including the month recorded allowed us to improve the estimation. Next, we excluded duplicate location values, region code, which was, for the most part, a mirror of the region values, although not entirely. Because region seemed slightly more accurate, we decided to go with that one. Next, we excluded columns with too many unique categorical variables. That is because a lot of models can only handle categorical variables with a small number of levels. So there were 6 values we didn't include in most of our general modeling. We did later, when it was appropriate, add these to models that could handle them, and we'll talk about that in the results. Finally, we excluded columns with a single unique value or an exact one-to-one copy of another column. The next thing we did is filling in the missing or invalid values for these 6 columns. Along with that, we created dummy variables, which were essentially variables that allowed us to tell the model whether or not this was data that was included in the original model or something that we had guessed at after the fact. This allows models to treat these differently. As part of this, we performed a test by, on most of these changes, running the model raw with only the raw data and then adding that single change. These have been ordered from most significantly improving the performance of a random forest to least significantly, or in this case, negatively impacting the performance of a random forest. Also, we performed this on XGBoost, which is a version of gradient boosting modeling, which we'll talk about later. You can see that for the most part, these changes were positive. There was only one category, one item here, that had negative for both models, slightly negative, and in our final modeling, we actually determined that when it was combined with other values, it did provide a positive impact. You can see, though, that for here, the most significant improvement for performance in random forest had a slightly negative performance impact in the XGBoost. This helped to show that the transformations, imputations, and other changes that we were making did potentially have a positive impact in the models. Next, we built the models using the general modeling data. For specific models that could handle it, we made specific changes. For example, for the random forest, there was one type of model which couldn't handle more than 53 unique categorical levels for a single column. But there was another random forest model, the H2O model, which would allow infinite ones. We were able to include many more columns in the H2O model because of that. Finally, when we arrived at our best model, we performed what's called model tuning. There are numerous parameters that you can set when creating a model. These included things like how far down a tree should be, the number of unique columns to try every time it's making a decision, and things like that. By giving it an array of values, we were able to determine the most efficient and effective model for determining and predicting new values. Finally, we used the models that we had created to complete our analysis and recommend further areas of investigation. That was our process, and now I'll hand it off to Austin. Thank you.
Due to the fact that this was a public competition that has had several rounds over the past few years, there are a number of groups and individuals who have already attempted to tackle this problem. To attempt to learn from these past groups, we scoured the web to find any information that may provide a base for our work so we can focus on continuing to build improvements into the past work instead of reinventing the wheel. One main source of information was a past Northwestern MSPA Predict 498 project that participated in the same data-driven competition in 2016. One of their primary goals was to provide a recommendation on the best prediction software, so they created many models on several different platforms. The three main platforms that group evaluated were R, Azure, and Angos. On the right, a slide from the group's final oral presentation is shown with the results of the various models they ran on each platform. R gave the best performance on several of the models, but all the solutions seem to give pretty respectable results. In addition to evaluating model performance, the team also addressed other aspects of the platforms, such as cost, skill sets needed, and the speed. Their work was valuable to us because it supported our finding early on that the random forests in R performed very well. So we focused on tuning those random forests in R and got excellent results, as we'll see later. The 2016 Capstone group concluded that R was the best choice given their circumstances, though they did comment on future changes that may alter their choice later on in the project, and Azure may be a good choice in the future. One of the key differences between the group's project and ours was that while one of their major goals was to create a recommendation on the best software suite to use, one of our primary goals was achieving a rank in the top 10% of competition participants. So the past group focused their efforts on fully evaluating each suite and provided an excellent comparison. However, they don't quite do as much diligence on fine-tuning their models to give a competitive edge like we've performed in this project. They also do not include their competition results, so we cannot compare their model performance with ours. Another great source of information we found was in public GitHub repositories of participants in the competition who decided to share their code publicly. Conveniently, the organization hosting the competition, Driven Data, has a public repository set up that contains the code of several past participants, some of which performed very well in the past competitions, as shown in the summary of the shared code and the ranking results in this slide. As we dug through the code, there were many different strategies. However, we kept seeing recurring themes of random forests and XGBoost models giving good results. So we pursued those the most. There are a number of platforms and languages that are available for predictive modeling and data exploration. We explored several of the popular options for both predictive modeling and exploration to find the most effective solution for our use case. When evaluating these tools, we have a couple of requirements in mind. For our EDA and dashboard tool, we want it to be easy to use and provide valuable insights into the data and also to look good. On the predictive modeling side, we want to make sure our number one priority is that it gives us accurate predictions and in this case scores well in the competition to get us into the top 10% of participants. We also need it to handle various data types such as numerical and categorical data and to be easy to modify if there are future changes in the data. There are three main tools that we explored for the EDA and dashboard products, and they were Tableau, Bokeh, and ggplot/Shiny. Looking at Tableau, the main pros were that it had a drag-and-drop interface that is extremely easy to use and is intuitive so visualizations can be created quickly and easily. It's also easy to publish dashboards publicly, and the hosting for public hosting the dashboards is free. However, some of the cons include the price in that the licensing for Tableau is quite expensive. And also we found that data cleaning required a separate program, so Tableau does now offer Tableau Prep. However, we found that it wasn't as easy to clean the data as it was in R or Python. Another tool we looked at was Bokeh, and this is a Python-based graphics library that's based on D3.js, which D3.js really provides some beautiful visualizations, but it's typically written in JavaScript. So Bokeh is nice because you can use the high-level language of Python, which also enables us to do the modeling and data cleaning in the same environment of Python. Some of the cons, though, are that obviously you need to know Python in order to create these graphics. And also one difficulty is in sharing these graphics once you create them publicly. You either need to host your own Bokeh server or you have to use a third party to deploy that visualization too. The last tool that we looked at for EDA and dashboards was ggplot, which is deployed using Shiny. So ggplot is one of the top libraries for R, and it's nice because it uses the grammar of graphics, which is a syntax that allows you to write advanced visualizations in a relatively easy to understand format. Shiny Dashboard provides a simple environment to deploy various types of content, such as interactive graphs. You can embed other types of charts, even Tableau can be embedded within a Shiny Dashboard. And it's also R-based, so if you do your data cleaning and modeling in R, it can be just as effective as if you did everything in Python, like you can with Bokeh. One of the cons, again, with any programming language-based solution is that you have to know the language. Another one was that we found that the interactivity was a little bit slower and much more limited than especially Tableau and even Bokeh. So it did look nice, but it just wasn't quite as easy to use. Here you can see our dashboard as used on a mobile device. Since keeping track of the latest reports of water point failures is important, we list key pieces of information on the most recent failures on the very first screen. For certain important variables, we provide a way for the user to examine the data with interactive plots created in R Shiny. Here we can see a user exploring the construction year. The performance is a little slow because it's running on a low-powered server. In the View Full Data tab, the user can explore the dataset and search for details they may find interesting. Both of the data viewing tabs use R's data table, which allows large datasets to be explored quickly and easily. In addition to the primary features of Shiny Dashboard, like the interactive Shiny Plot and the data table views, another great feature is that we can easily embed Tableau dashboards like this, which make up the remaining tabs. As mentioned, we found Tableau to be very easy to work with for creating interactive visualizations, including maps, which gave better performance than the other solutions considered. Here is one of the maps created in Tableau that has several embedded functions to select, search for, and explore individual data points. As seen, here's one of the select functions that allows a subset of the data points to be selected and can view details on them. You can also search the map if you're looking for specific points that you know about, or zoom into tiny points on the map to see more details or get clarity if it's too hard to see from far away. Some aspects of our dashboard are a little rougher on the edges, but with additional work, they can be customized and extended with only a small amount of effort. We also have a website for our project at daftpumps.com. Here, we provide links to our project code hosted on GitHub, as well as access to the dashboard just shown. When not on a mobile device, the dashboard can be viewed larger on a desktop browser. On the predictive modeling side, we looked at options in Python, R, and SAS Enterprise Miner. Both Python and R are programming languages that each have a large number of modules available. Though we use several modules in Python and R, we'll address two of the Python modules separately, as their approaches are distinctly different. In Python, scikit-learn is a popular platform that offers a broad range of predictive modeling techniques, including random forests, support vector machines, decision trees, regression, and many others. The nice thing about scikit-learn is that these models are very similar syntax, so trying out new techniques is relatively easy. Also, since we're in Python, we can do the data exploration, cleaning, and modeling in the same Python environment without needing other tools. A challenge we encountered was that many of the techniques offered could not handle categorical variables out of the box, so the user must handle those themselves. Another Python-based platform is TensorFlow, which was developed by Google. TensorFlow allows the user to create neural network models that have gained popularity and have received publicity for their success in large-scale applications. TensorFlow models do not come with many out-of-the-box procedures, so additional work is required to build an effective model when compared to the other solutions. Coming to R, we tried out several predictive modeling libraries like Random Forest, H2O, and others, which will be discussed in depth a little bit later. As we saw in the past projects we reviewed, the out-of-the-box models seem to perform well in R, and the categorical variables were easier to handle. Like Python, there are large online communities, so there are many free resources available for learning. Though R is a popular tool for data scientists and the statistics community, there have been some criticisms that R is not a production language, and when predictive models developed in R need to be deployed into production, they are often rewritten in other languages. The last tool we've looked at was SAS Enterprise Miner. Enterprise Miner is based on the SAS programming language, but provides a convenient drag-and-drop interface for data exploration, cleaning, and modeling. On the right, you can see a screenshot of a workflow in Enterprise Miner that imported, cleaned, trained, and validated the data for this project on several different predictive models, including random forests, decision trees, and neural networks. The workflow also compared the results of the models and scored the test data on the best performing model. Having a similar workflow in Python or R would have required many times more time and effort to code. For many organizations, Enterprise Miner may provide users with most of their analytical needs. The instance we used was provided by SAS On Demand for academics and ran in the cloud, which gave good performance when training models. This was the only non-free predictive tool that we used, and though we were successful in cleaning the data and running models, the setup had some peculiarities which made installation difficult. Also, though the interface is drag and drop similar to Tableau's, the responsiveness was much slower and made it more difficult to do tasks that should have been easy. Ultimately, we found R to be the best modeling tool, in part because it had well-chosen default values, so we saw success early on. This allowed us to continue to iterate and improve our performance, as you will see later in the model comparison. Next, Tyne will explain the predictive modeling techniques we used.
Okay, I'm here to talk about models. There is no glue sniffing or movie watching involved in these models. This is the exciting type of model, the mathematical models. There are lots of different mathematical models for solving the kind of problems we're trying to solve. But you have to figure out what kind of problem you're trying to solve. So we know that our data is a multi-class classification problem where we're trying to assign not a number, right? Between like 1 and a million. It's more of is it functional? Is it functional, needs repair, or is it non-functional? So we call that a multi-class classification, and that narrows us down to these sort of classification algorithms. That Microsoft Azure is nice enough to publish this slide here. The first kind of model we looked at is decision trees. Decision trees has nothing to do with trying to decide what kind of tree you need, for maybe a holiday celebration. It's really more about the structure that you create as you go through different decisions about your data. Like if you're to look at your data, if you're trying to figure out if your shirt is wet, with this handy slide here, you might first ask, well, are you outside? If you're not outside, then probably your shirt isn't wet, unless maybe you're trying to drink something, and then we assign a 5% chance that your shirt is wet. If you're outside, well, is it raining? If it's not raining, then it's only 10% chance that your shirt is wet. If it is raining, are you wearing a jacket? If you are, then there's a 20% chance you're wet. Maybe some rain gets through there. If you're not wearing a jacket and it's raining, then you are definitely wet to some degree. Each of these is sort of a branch on a tree, right? You're branching the decision process down here. So decision trees are pretty basic mode. They can run into some problems with overfitting if you go too far down, which means that it might work on the test data that we have, but it won't work on the real data, the data we're trying to predict. This actually is an example of a decision tree from our data, right? If it starts off with sort of quantity, and then looks at the type of water point it is and the amount of water that comes out of it and the age, sort of splits along here, and you can end up with different values. We didn't end up going with a decision tree, but this is really important for what we did end up going with, which was a random forest, where this picture kind of makes sense. Random forest is a bunch of different decision trees that you build, and then you sort of average them all out to result in sort of one tree to rule them all. That's basically based on averages, right? So you have all these decision trees that maybe they get overfit, but when you average them all out, the overfitting problems kind of go away. So random forest is what we ended up using, actually. We also looked at GBM, which is gradient boosting machine, and extreme gradient boosting machine that are sort of ways to approach usually classification trees and decision trees like we did, and sort of deal with a problem that is sort of known as local minima. So this is a really simple example, right? This is a two-dimensional example of local and max and global minimum. What can happen as let's say you start your data search here, and you go to the right a little bit. Oh, it's getting lower, which is, if you're looking for a minima, getting lower is important. And you keep going along this curve, and you get down here, and you're like, oh, look, I found the minimum. If I go more to the right, it gets higher. This must be the right answer. Except you don't know about the data over here, right? Or maybe this data goes way out here, and there's a minima. There's even a lower minima over here. So gradient boosting machines and XGBoost sort of have algorithms to deal with this problem, right? So that they can sort of locate other areas of minima and avoid the problem of getting stuck in a local minimum, which can happen pretty easily. In addition to that, we looked at some other approaches. We looked at something that we call deep neural networks, right? And neural networks are based on something called the perceptron algorithm, which was invented by Frank Rosenblatt at Cornell's Aeronautical Laboratory in 1957. It was a project for the Navy to identify images, right? So he's able to, with this algorithm, he's able to divide the data into two areas. Maybe they draw a really complicated line to divide the data. And this is actually, before the advent of general purpose computers, right? So this is, a computer custom built to run this algorithm, which looks really daunting. Neural networks sort of evolved from that initial perceptron. So, a neural network in general sort of works like this, right? It has like an input layer, right? And in the case of visually detecting things, you might create a grid of data, right, that represents, different shades of white to black. And then you put that through one or more hidden layers where there are different weights played on it, and it takes it to an output layer. The real breakthrough for deep neural networks for neural networks was the invention of the back propagation. So you had this thing that would go through this way, but you need to be able to adjust the weight. So the back propagation actually looks at the success of the prediction over here, and then it sends input, for lack of a better word, back through the layers, going backwards, and it adjusts the weights so that when it comes back through again, maybe it's a little bit better, right? And in a neural network, you do this process, thousands of times, right? And in a deep neural network, one thing is you might have more layers than you might do with a regular neural network. But you're also, some of these inputs now might be, things that you've done to the input data, the initial input data, that maybe they have their own small neural network, right, that you're putting into here. This an example with this is sort of image recognition, where you might, do things like edge detection, where you look for, all the edges that are perfectly straight across, for instance. So you would have all these inputs onto all the different edges that go in as one of the input layers in this model. So it's adding extra data to that. Deep neural networks are really great for image recognition. They're used a lot for voice recognition or text, sort of pattern recognition like that. They did not work out so well for this data. We pumped the data through a deep neural network with TensorFlow, and we got a 0.52 in the competition. 0.52 is a little bit below what you would get if you just assigned everything functional. It's a little bit worse than just guessing that everything works. We did hundreds of iterations of deep neural networks trying to tune the parameters to get a good result, but nothing really got up to a point where we would want to submit it again. It just was not a successful algorithm for us. That doesn't mean that this couldn't solve it. It just means that we weren't able to solve it in the time we had, and it wasn't looking like a fruitful avenue of pursuit. We also looked at bag of words. So bag of words is an approach that takes a look at all the text that you have in a row, right, and sort of and then all the text that's in the entire data set, and sort of figures out the frequency of the words, and if a word keeps showing up and it ends up meaning something that's predictive, then that helps, right? So we did we used n-grams, right? So n-grams are a big part of bag of words. You would take your text and break it into how many you would count each individual occurrence of one word, and then you would do a bigram, right, a two level n-gram, and you would look at when do two words occur together, right, and then you might do trigrams and look for three words, and then another trick we looked at was interaction terms. So you would want to know when does a text have 1 and 4 in this visual example in the same row. It's just a way of sort of accounting for words that might belong together, but maybe they're separated by a lot. And that is actually the end of the models. So the bag of words and the some of this other stuff we looked at was actually built on top of our more successful models. So we took like a random forest approach and tried a bag of words approach on using random forest as the prediction algorithm. But now I'm gonna hand it over to Dan to talk about how the models did and some other stuff with our data here.
Hi, this is Dan, and I'm going to talk about comparing the models. We did two types of comparisons for most of our models. The initial one, called a holdout, was when we would take 25% of the training data, hold that out when we were training the model, so we were only training it on 75% of the data, use that model to predict the remaining 25%, and compare that prediction with the actual values. This allowed us to identify, without submitting to driven data, models that were performing well. You can see from this that the first model we tested against was all pumps being functional. Functional was the state with the highest percentage, so the simplest model is just to assume that they're all that. We then compared all other models against that. There was a hierarchy of models with decision tree providing a 27% improvement, but there were a lot of other models that performed even better than that. Gradient boosting modeling, the simple version provided in R, performed a 0.7058. But when we did XG boosting, a different library for gradient boosting modeling, it provided a 0.8083 in the driven data competition. This was a fairly significant improvement from the gradient boosting modeling. Finally, we had two flavors of random forest that did well. The R random forest performed 0.8226 in driven data, and the H2O random forest performed 0.8248. Both of these did very well, but H2O random forest, with its ability to include factors with more than 53 levels, was able to use more information to generate its estimates, its predictions, and thus ended up being the winning model. You can see from here the different types of model we performed. We started with a decision tree. We used random forest, which did very well, and so we spent a lot of time improving on the random forest modeling. We didn't, though, constrain ourselves to that, and we included a lot of other types of models as we went along. These used much of the same information that we used in generating the random forest models, and as you can see, none of them performed as well. I talked previously about two specific technologies we used for random forest. And here you can see them. These were what we considered our winning models. Regular R random forest performed at the highest at 0.8226. You can see here that there is a pretty general trend upwards for the R random forest. With the H2O random forest, initially, we hadn't thought it would perform as well. When we provided it with the same data that the R random forest was using, it simply wasn't able to perform as well. We weren't exactly sure of the reason for this, but we had an estimate that it had to do with some differences in how it's decided which factors were most appropriate to include at every level. Near the end, when we had made about as many improvements as we could to the R random forest, we also started to pull in the high level factors, the ones with more than 53 factor levels. R random forest didn't really allow for doing that. It required us to do a lot of work to try and get those to work. But H2O random forest allows you to include them, and as you can see, it provided a much greater score. This is because it is using a lot more information. And because of that, we ended up selecting H2O random forest as our final best model. The differences between R random forest and H2O random forest were not huge, but they were somewhat significant. R random forest was faster to predict when a model is built, but it was much slower to build the model. Like I said before, it could only handle categorical variables with 53 unique levels. It didn't do native multi-core processing, which is how most modern computer chips are designed, and so it leaves a lot of performance improvements. You can do these with third-party libraries, but they're not great. Finally, it had a different way of splitting leaf nodes for categorical variables, and that's what we suspect was causing our improved performance when we just did the general data. Now, H2O random forest on the other side is much faster to build models, although it was slower to predict once the model was built. But it does allow multi-core processing, and it has a progress bar, which, when you're waiting for 30 minutes for it to finish, is nice. Finally, it allowed for an unlimited number of levels of categorical variables, which is ultimately what allowed it to win, since it simply had more information. As you can see, on the left, we have what the importance of all the variables for the generic R random forest. Quantity group, latitude, longitude, elevation, age were all marked as important. On the right, we had what the H2O random forest marked as important. And you'll notice LGA, that's one of the categories that is not included because it has more than 53 levels, was marked as second most important. LGA is a combination of region and district code, which are down here, and it is highly correlated with latitude and longitude, which are up here. As you can see, all of those dropped in their rankings. So by using LGA, H2O was able to perform better, but it was also able to pull information that was not necessarily that was available in other columns, but it appeared to do it in a way that improved its performance. Finally, when you look at this, there's the types of data changes we made and how those improve the performance. So for example, on the left side here, imputing the variable, these are the differences in scores when we made a change that imputed a variable. These are also split by H2O in random forest and R random forest, with the blue dots representing the R random forest. And you can see that for the most part, the H2O random forest ones are positive. That's because a lot of the experimentation that we did had been done in the R random forest, and because they're similar types of models, the benefits you'd see are the same in both.
So how'd we do? Our final classification rate was a 0.8248, which ranked us at 50 out of 5,235 competitors. The highest classification rate was a 0.8285, a difference of only 0.0037 from our final score. A classification rate of 0.8248 means that our final random forest model correctly predicted the functionality of about 82% of the water points included in the data. Did we meet our goals? As you may remember, we set out this project with 3 major project goals. The first project goal was providing a consolidated view of the most up-to-date publicly available information regarding this project, the dataset, and prior work performed by other teams. We feel like we've completed this project goal as we did discuss all of the publicly available data that we found, as well as the previous MSPA project. We also utilized these projects to build upon them and improve our models. The second goal that we had was scoring within the top 10% of participants in the driven data competition. We actually ended up scoring in the top 1% of the competition, so not only did we meet, we exceeded this goal. Finally, our third goal was to deliver a service-focused dashboard to show how we plan to utilize the model to direct our resources if we win the bid. As you saw in Austin's previous presentation of our dashboard, we've also met this goal. So what does this all mean? Random forest was found to be the modeling technique of choice and is suggested for future use in water point classification modeling. There are a few notable variables identified in the models and suggested for future consideration. Age of the water point, population surrounding the water point, elevation, and latitude and longitude. Consideration of these variables in the classification of the pumps appears logical. The older the pump, the higher the potential likelihood of needing repair or breaking. The higher the population around the well, the more use, which could offer more wear and tear to the pumps. And different locations and elevations could open the pump to more wear and tear from weather and other geological factors. However, due to the poor overall quality of the data, Daft Pumps does not consider this a project for a good business opportunity. So what's next? The poor quality of the data, however, can be seen as its own business opportunity. Daft Pumps recommends for this new opportunity 2 main items. Number 1, we propose to offer to create, deploy, and manage a small cellular data connected, low power, and solar rechargeable monitoring devices for every public water point in Tanzania. This will allow up-to-date reporting on the status of all water points, which will also enable Daft Pumps to start building much more powerful models based on time series analysis from the data collection. We also propose an SMS-based mobile app that would allow users to report status directly, either by exception reporting, maybe run through the government, or local water wardens just to update us on all of the data. If you have any questions on this presentation and our final project, as well as suggestions for future projects, please feel free to email any of us. Once again, we'd like to thank you for your time and consideration of this project and hope that you would consider our future recommendations. Thank you so much.